Hello, this is Lee Donggun from Group 4 of Farshod Mosh's Math 1A class in 2017 spring quarter, and I'm going to do a presentation about our chapter 4, which is optimization and related rates. Before going into the chapter, let's look at what this chapter is for. To able to answer a real-life problem, a mathematical model that can almost describe the problem are built by scientists. The more precise model means the more difficult the mathematical formula is needed. But in our case, we'll be looking at more simpler model in the study. Our first will be optimization of the function. It is when the rate of change is zero. It is the moment when there is no change in the value of the function. The point at which the rate of change is zero is called maximum or minimum point. The second is related ratio of the function. It is when the rate of change is not zero and the function keeps increasing or decreasing. And another would be symmetry of the function. It is used to maximize an expression of two variables. It can be done by converting broken symmetric problem to a symmetrical problem. Now, before going to the chapter, let's see the recommendation. It is recommended to review a parametric equation and then Newton's law from chapter 2 and the rational zero test and some techniques of solving polynomials. However, I personally recommend to review the law of acceleration and gravity, especially for our homework assignments, because it is dealt in quite a lot of questions. Now, let's take a look at the steps to solve optimization problem. The first step to find a solution for optimization problem would be to find the relation equation of the problem. And then we can find the optimization equation of the problem. And then we can find one variable in terms of the other form of relation equation and plug it back to the optimization equation. And using the function, we can differentiate it and assume that it equals to 0 because when it's equals to 0, the point will be the maximum or minimum point will be our optimal point. And then using the function derivative of the function, we can solve for the variable. And then lastly, we can plug it into relation equation to solve for the remaining variable. Now, let's take a look at the problem 1 from our chapter paper by using the steps to solve the optimization problem. The sum of the two numbers is k, and then the product is maximum. What are the numbers? The first step to find relation equation. The relation equation is x plus y equals to k. It is given in the question. The second step is to find optimization equation. The product of x and y equals to maximum. It is also given in the question. And the third step is to find one variable in terms of the other. In this case, we found y in terms of x. So y equals to k minus x. And we can insert this into optimization equation for the next step. And it results as x bracket k minus x bracket equals to maximum, and our final function will be minus x squared plus kx minus maximum. And fourth step will be to find the differentiation of this function. And assuming that it equals to 0 for the maximal or minimal point to find the optimal result of the function. And the differentiation of the function is minus 2x plus k. And we can see that x equals to k over 2. And our last step will be to plug in the result we got from step 4 to relation equation to find the remaining variable, which is y. So k over 2 plus y equals to k. And we can see that y equals to k over 2. We can also solve this problem by using the idea of symmetry. Since x plus y equals to k is same as y plus x equals to k, and the variables are interchangeable with each other, and we can see that this equation is symmetrical. And since the result does not change when the variables are interchanged with each other, it means that the variables must be same as each other. So the result would be x equals to y equals to k over 2. Now let's take a look at the steps to solve related rates problem. The first step would be to find a relation equation and rate equation. And then the second step would be to differentiate the rate equation. And in our third step, from relation equation, we can solve one variable in terms of the other and substitute it into differentiation of rate equation. And at all, we can solve for the unknown. Now let's take a look at the problem 3 from our chapter paper by using the steps to solve the related problems. At point A, a stationary observer looks at a moving object at point B, who's moving away from point O at the rate of v. The first question is how fast the separation between A and B changes when B is from point O. And second question is how fast the angle between the line of sight and x-axis changes at that time. Now let's solve the first question first. The first step to find an answer for question 1 is of course to find relation equation and rate equation, which are the same in this case, and it's x squared plus y squared equals to s squared. S represents the distance between two variables. The second step would be to differentiate the function. It will result in 2x x prime plus 2y y prime equals to 2s s prime. Since observer is stationary and its rate of change, which is x prime, is 0, the final result of the function is y prime equals to s prime. And in our third step, we can insert the result into our rate equation. And since s equals to square root of a square times b square by Pythagorean method, bv equals to s prime square root of a square times b square. And the fourth step would be to solve the equation, and then we can find our answer, which is s prime equals to bv over square root of a square times b square. The fourth step to solve the second question is to find relation equation and rate equation, which are also the same in this case, which is y equals to a tangent zeta. And our second step will be to find a differentiation of the function, which is y prime equals to a secant square zeta times zeta prime. And the third step would be to insert the result into rate equation. And since a secant square zeta equals to square root of a square times b square, y prime equals to square root of a square times b square times zeta prime. Now the final step is to solve the problem, and then we can find our answer, which is zeta prime equals to y prime over square root of a squared times b squared. This time, let's solve a related rates problem by symmetry. It's the problem 5 from our chapter notes. A ladder L meters long leans against the wall. The end on the floor slides up away from the wall with speed dx over dt. When it is a meter away from the wall, first, how fast the other end approaches the floor. Second, how fast the angle between the ladder and floor is changing at that time. For the first question, which is to find the other corresponding rate of the variable, first the relation equation is x squared plus y squared equals to L, the length of the ladder, squared. And then when we differentiate it, it becomes x times x prime plus y times y prime equals to 0. Since L is a fixed number with no change in rates, it is deleted. Next, when we find y prime in respective of x and x prime, the equation we get, or the answer, is y prime equals to negative bracket x over y bracket x prime. The negative sign of the equation shows that the other end gets closer to the floor. For the second question, which is to find the rate of the angle, our relation equation is tangent zeta equals to y over x. Then after turning x over to the left side of the equation and differentiating it, we get x prime tangent zeta plus x secant square zeta bracket d zeta over dt bracket equals to y prime. And from the first question, x prime equals to negative bracket y over x bracket y prime, the negative reciprocal of the answer, we can get the equation x prime equals to negative y prime tangent zeta. If we insert this equation into the former equation, we get x secant square zeta times d zeta over dt equals to y prime bracket 1 plus tangent square zeta bracket at the end. Since secant square is same as 1 plus tangent square zeta, the final equation we get is x bracket d zeta over dt bracket equals to y prime. So our answer for the rate of the changing angle is y prime over x. Now let's take a look at some questions from our homework assignments, and these questions are chosen by my Android app. It chose for the optimization questions number 7 and 8, and for related rate questions it chose number 2, 9, and 18. Let's take a look at optimization problem number 7. The question is, the upper right-hand corner of a piece of paper 12 inch by 8 inch is folded over to bottom edge. How would you choose x to minimize y? And this is the picture of the problem. First, let's find the relation equation. Since triangle CDE is similar to triangle BCA, and line CB equals to x, z over x equals to 8 over 4 square root of x minus 4, and z equals to 2x over square root of x minus 4. Secondly, let's find optimization equation, which the function is y squared equals to x squared times plus z squared. Third, let's insert the result into our function, where z squared equals to 4x squared over x minus 4. The function is as it goes as y squared equals to x squared plus 4x squared over x minus 4. And the final result is x cubed over x minus 4. And then we can solve this function by differentiating it and then leading it to 0. And 2y prime would equal to 0, and it will equal to differentiation of the function, which is 2x squared bracket x minus 6 bracket over bracket x minus 4 bracket square. And the answer is that the x is either 6 or 0. However, when x is 0, it means that the paper wasn't folded. So the answer goes against the question. So y is at its minimum value when x is 6. Now let's take a look at the optimization problem number 8. The question is, or the problem is, Fermat's principle. A ray of light will travel from point A in air to a point B in the water by path ACB that minimize the time taken. Show that sin zeta 1 over sin zeta 2 equals to V1 over V2. This equation is known as Snell's law, where V1 and V2 are the speed in air and water. And the picture of this question is this. Now for first step, we should find relation equation. Line AC equals to square root of x squared plus a squared, and the speed for it is v. And for line CB, the distance is square root of bracket c minus x bracket square plus b square, and speed for it is v2. And the optimization equation, since time equals to distance over speed, the function tx equals to square root of x squared plus a squared over v1 plus square root of x bracket c minus x bracket square plus b square over v2. And thirdly, let's find the differentiation and then insert it. So the differentiation of the function tx is x over v1 square root x squared plus a squared plus minus bracket c minus x bracket over v2 square root bracket c minus x bracket square plus b square, and it equals to 0 by optimization rule. And since sin zeta 1 equals to x over square root x squared plus a squared, and sin zeta 2 equals to c minus x over square root bracket c minus x bracket square plus b square. And then if these two equations are inserted into differentiated equation, it is same as sin zeta 1 over v1 minus sin zeta 2 over v2 equals to 0. And then we can lead these into our answer, which is sin zeta 1 over sin zeta 2 equals to v1 over v2. And now let's take a look at the related rates problem number 2. A particle at A moves toward point P on x-axis and between 0 and B with speed of v, and then moves toward B at speed u. Find location of point P such that its trip from A to P and to B is the fastest. Now this is the similar question as the previous one. And the graph for this question is like this. Now for relation equation part, same, since time equals to distance over speed, and the distance 1 L1 equals to square root of a square plus x square, and its speed is v, and for line 2 L2 the distance is b minus x and its speed is u, we can find the function for t, which equals to square root of a square plus x square over v plus b minus x over u. And second step, to differentiate and solve. So differentiation of the function is 2x over 2v square root a square plus x square minus 1 over u when it equals to 0 by optimization rule, because it is told to find the fastest time. And then if we solve this, it'll turn out as ux equals to v square root of a square plus x square, and then u square x square equals to v square a square plus v square x square. And then by turning it over, we can see that v square a square equals to x square bracket u square minus v square. So x square equals to v square a square over u square minus v square. So finally, x would equals to square root of v square a square over u square minus v square. So the point P, which makes the trip from A to P to B the fastest, is point P square root of v square a square over u square v square, comma 0. Related rates problem number 9. The figure shows a circle with radius 1 inscribed in the parabola y equals to x square. Find the center of the circle, and the picture is as shown above. For this question, we gotta find the differentiation of the parabola y equals to x squared to derive the relation equation we need. So when point A is a comma a square, the slope of the line L is 2, and we can find this by differentiating the parabola function, which is y equals to x2, and the derivative of it will be y prime equals to 2x. So equation of the line L will be y equals to 2 bracket x minus a bracket plus a square. And final equation will be y equals to 2ax minus a square. And when point B is 0, b, the distance between point B and line L is the absolute value of minus b minus a square over square root of 4a square plus 1 equals to 1, because it's a unit circle. And then second, but lastly, we can solve the question. So the absolute value of minus b minus a square equals to square root of 4a square plus 1, and if we take out the square root of the right equation, it will be b squared plus 2ab plus a to the power 4 equals to 4a squared plus 1, and a to the power 4 plus 2a squared bracket b minus 2 bracket plus b squared minus 1 would equals to 0. And for the equation to result in one point, which is the center of the circle, the discriminant of the function has to be 0. So the discriminant of the function, which is minus b minus 2 square minus bracket b square minus 1, and it has to be 0. So at the end, it'll be minus 4b plus 5, and b will be 5 over 4. So the center of the circle is 0, 5 over 4. Last question, which is related rates problem number 18. And point P at 12 is moving toward origin at the rate of 1 meter per second. When point Q at 0 moves in y-axis above with velocity of 1.5 meter per second. And the graph is as shown above. So the questions are, how fast the separation between the points changes after 4 seconds, and how fast the angle of the line from P to Q with x-axis is changing after 4 seconds. So for the first question, how fast the separation, let's take a step-by-step solution. First, relation equation is x squared plus y squared equals to r squared. And then let's differentiate it. It's 2x x prime plus 2y y prime equals to 2r r prime. And then r prime will be 2x x prime plus 2y y prime over 2r. And then we can insert the numbers at the changes after 4 seconds. So 2 times 8 times minus 1 plus 2 times 6 times 1.5 over 2 times 10 will be our r prime. And our r prime, which is d over dt, is 0.1 meter per second. Our second question, how fast the angle of the line from P to Q with x-axis is changing after 4 seconds. First, the relation equation. The relation equation for this problem is tangent theta equals to y over x. And then if we differentiate this function, we will get secant squared theta times theta prime equals to y prime x minus x prime y over x squared. And we can insert the numbers during this 4-second period, and our theta prime would equal to 1.5 times 8 minus 6 times minus 1 over 8 squared times altogether multiplied with cosine theta squared. And the result would be that theta prime equals to 0.18.
Before we close this chapter, let's take a look at one of the exam questions. Our exam question number 3 was from related rate problem number 4. The question was to cut A and B are connected by a loop of 39 meter long that passed over a pulley B. Cut A is being pulled away from Q at a speed of 2 meter per second. How fast is cut B moving toward Q at the instant when cut A is 5 meters from Q? The picture for the question is as shown above. First, we have to find the missing or required numbers at the instant when cut A is 5 meters from Q to solve the problem. Since the height of the pulley is 12 meters and A is 5 meters away from Q, the loop connecting A and P is 13 meters long, and the remaining loop that is connecting P and B would be 26 meters long. Then we can find the distance between B and Q by subtracting square of height from square of the loop length connecting it. Thus the distance would be square root of 532. Second, we need to find the equation for the lines needed to solve the problem. Those would be the equation for R and Y. Then we can differentiate the first equation. When we differentiate it, it would it will come out as 2 L times L prime equals to 2x times x prime plus 0. And if we insert the numbers we found we found out we found out in the first step, L prime will equal to 20 times 1 over 26. So the rate of change or R is 10 over 13. Since the length of the loop does not change, the rate of change for the loop connecting P and B will be minus 10 over 13. Lastly, we can insert the result from the step 3 to the differentiation of the other remaining equation for y. The differentiation of the function is 2y times y prime equal to capital L times capital L prime minus 0. Same as before, if we insert the numbers from step 1 to the function, y prime will equal to 26 times negative 10 over 13 times 1 over square root of 532. So the answer, which is the rate of change for y, is negative 20 over square root of 532. When simplified, negative square root of 532 over 33.